Today we will discuss some numericals. The first one is an electric dipole of length 4 cm when placed with its axis making an angle 60 degree with uniform electric field experiences a torque of 4 root 3 Newton meter. Calculate potential energy of the dipole if it has a charge of plus and minus 8 nanocoulomb. So what is given is a dipole is there. 4 centimeter is the length of the dipole. It is experiencing a force 4 root 3 Newton meter inside an electric field, and dipole moment vector makes an angle 60 degree with the electric field direction. So we already studied torque acting on a dipole when it is placed in electric field. Tau is equal to Pe sin theta. So here it will be 4 root 3 is equal to Pe sin of 60. Sin of 60 is equal to root 3 by 2. Therefore 4 root 3 is equal to Pe into root 3 by 2. Therefore root 3 cancel. Therefore we will be getting Pe is equal to 8 units. So the question is calculate the potential energy of the dipole if it has a charge of plus and minus 8 nanocoulomb. So we already studied potential energy of the dipole. U is equal to minus Pe cos theta. Pe is already obtained, that is 8 units, SI units. Therefore U is equal to minus 8 into cos of 60. So cos of 60 is equal to 1 by 2. Therefore minus 8 into 1 by 2. Therefore potential energy is equal to minus 4 joule. So this will be the answer of this question. Let us discuss another question. So the question is like this. How much work is required in turning an electric dipole from a position of most stable equilibrium to a position of most stable equilibrium to a position of most unstable equilibrium? So you can read the question once again. It is correct only most. So how much work is required in turning an electric dipole from a position of most stable equilibrium to a position of most unstable equilibrium? Then the question arises, what is most stable equilibrium? When electric dipole moment and electric field are in the same direction, that configuration is the stable equilibrium. Theta is equal to 0, potential energy is equal to minimum, that is minus Pe. When electric field and electric dipole moment vector are opposite to each other, angle between electric field and electric dipole moment is 180 degree. At that particular configuration is called unstable equilibrium. Potential energy is maximum. So potential energy is maximum means the system is not stable. Potential energy minimum means the system is stable. So the question is, how much work is needed to turn a dipole from most stable equilibrium to most unstable equilibrium? So that means this vector, this dipole, I have to turn 180 degree like this. So that means this positive charge, when I turn 180 degree, it will come here in the left hand side. So how much work is needed? So the simple logic we already studied, the work done is equal to change in potential energy. So in this case it will be potential energy final minus potential energy initial. So potential energy final will be Pe, final potential energy at the 180 degree configuration, minus potential energy initial will be minus Pe. Therefore Pe minus Pe, that will be 2 Pe. That will be the work done to turn the dipole from most stable equilibrium to most unstable equilibrium. So another equation we study, the work done, W is equal to Pe into cos of theta 1 minus cos of theta 2. Using this equation also we can find out the same. So here what is theta 1? Theta 1 is equal to 0 and theta 2, the final angle, theta 2 is equal to 180 degree. Substituting these, we will be getting W is equal to Pe into cos of 0 minus cos of 180. So we already studied cos of 0 is equal to 1 minus cos of 180 minus 1. Therefore it will be Pe into 1 minus of the minus plus 1 plus 1 2. Therefore 2 Pe. So answer is 2 PE. Let us discuss one more problem. You can read the problem. Two identical dipoles A, B and CD, each of dipole moment P, are kept at an angle 120 degree as shown in the figure. What is the resultant dipole moment of the combination? That's the first part of the question. What is the resultant dipole moment of the combination? If the system is subjected to an electric field E directed along the x direction, what will be the magnitude and direction of the torque acting on this system of dipoles? So there are two questions. First one is, we have to find out resultant dipole moment of the combination, and then we have to find out the magnitude and direction of the torque acting on the combination. So first of all, we have to draw the figure which represent the situation. Two dipoles are there. One is AB and second one is CD. They are at an angle 120 degree. They are at an angle 120 degree means the dipole moment vectors are at an angle 120 degree. The dipole moment vector of this dipole will be upwards, because dipole moment vector is always acting from negative charge to positive charge. Therefore, dipole moment vector of the first dipole will be upwards. The second vector is acting like this. So the dipole moment vector is acting in this direction CD. Therefore, dipole moment vector of the second one is like this. So these two vectors are at an angle 120 degree. So what will be the resultant? Parallelogram law of vector addition helped me to find the resultant. According to parallelogram law of vector addition, the resultant vector, dipole moment vector PR, is equal to root of P square plus 2 P into P cos of 120. Because these dipoles are identical, therefore dipole moments also magnitude wise same. So P square plus 2 P into P square cos of 120, 2 P square plus 2 P square into minus 1 by 2. So this 2 and 2 cancel. 2 P square minus P square, it will be P square only. The square root of P square will be P. So the resultant of the dipole moment is nothing but P, the dipole magnitude of the dipole moment of any dipole. We have to find not only the resultant but also the torque acting on the resultant dipole. So in order to find out torque acting on the resultant, we have to find out the angle between resultant dipole and electric field. Electric field is acting in the x direction. This will be the angle between resultant dipole and electric field. Let it be theta. So we have to find out theta. In order to find out theta, the first of all we will be finding out the direction of the resultant from first vector. So let us consider this as the first vector. Direction of the resultant from first vector we can find out. Last year we studied how to find direction. Tan alpha is equal to B sin theta divided by A plus B cos theta, where A, B are the first two vectors. Here the first vector is dipole moment P, second vector is also dipole moment P, therefore it will be P sin of 120 divided by P plus P cos of 120. Now from the denominator P can be taken out and P cancels from numerator and denominator, then what remains is sin of 120 divided by 1 plus cos of 120. Sin of 120 is root 3 by 2 divided by 1 cos plus cos of 120, it will be minus 1 by 2. So minus 1 by 2 means 2 minus 1 by 2, 1 by 2 only, 2 goes up and 2 and 2 cancels, what remains is root 3. So tan alpha is equal to root 3, therefore alpha is equal to tan inverse root 3, that will be 60 degree. What is this 60 degree? This angle is 60 degree. The resultant is acting at an angle 60 degree from the first vector. So if this angle is 60 degree, we already know that this angle will be 30 degree, because this is perpendicular 90 and all together this much is 120 degree. Then what remains is this much is 30 degree, and this plus 30 will be 60, because this angle is 60. This plus 30 is equal to 60. That means angle between the resultant and electric field is 30 degree. So angle between resultant and electric field theta is equal to 30 degree. From that particular thing, I can find out the torque acting. What is the torque acting on the resultant dipole? Torque tau is equal to PRE sine of theta, where theta is the angle between resultant and electric field that we already obtained 30 degree. Therefore, PRE into 1 by 2, PRE divided by 2, that will be the torque acting on the resultant dipole. Now, one more question is there in that, one more problem is there in that question. What is the direction of the resultant? Magnitude of the resultant torque we already obtained, tau is equal to PRE divided by 2. How to find out direction of the resultant? This equation can be written as tau is equal to PR cross E in terms of vector. Since this is a vector product, cross product, we have to find out the way of finding the direction of the cross product. In order to find the direction of the cross product, we have to curl the fingers from first vector to second vector, then the thumb indicate the direction of resultant. In this particular case, first vector is PR, second vector E. I have to curl my fingers from PR to E. That means thumb indicate the direction of the resultant. That means the resultant will be acting into the paper. So this particular system will rotate like this because resultant vector is acting into the paper.